Hello everyone, and welcome to today's presentation. I'm excited to have you here. Today we'll be discussing a critical issue related to centrifugal compressors, specifically, the hot startup problem. The title of our session is Hot Startup Issue of Centrifugal Compressor, and we'll also touch on some solutions and best practices. Over the next few minutes, I'll walk you through the key challenges and potential approaches to address this issue effectively. So let's get started. Let's talk about what happens at high synchronous vibrations, specifically at the 1x speed, which is tied to the first resonance speed and the first bending mode of the rotor. When the rotor vibrates intensely at this frequency, it creates a high probability of rubs occurring. These rubs are especially likely in the rotor midspan area, where the clearance between the statoric parts, such as the interstage labyrinths, and the rotor itself is very small. This very low clearance means that even a slight vibration can cause contact, and if this contact happens repeatedly, it can lead to serious damage. In fact, the damage can be catastrophic, potentially compromising the integrity of the entire machine. So the key point here is that these high synchronous vibrations at critical resonance speeds significantly increase the risk of rubs, which can severely harm the equipment. Understanding this helps us appreciate the importance of managing rotor vibrations and avoiding operating conditions that could lead us into these dangerous resonance zones. In this slide, we're looking at the simple arc-like deflection of a rotor in its first bending mode. What this means is that the rotor bends in a smooth, single curve, kind of like a gentle wave. There's usually just one hump or antinode, which is the point where the displacement is the greatest. Now, the key thing to remember here is that this maximum displacement occurs at the tip of the rotor, the part farthest from the central axis of rotation. This is important because it's where the rotor experiences the most movement during bending. Conversely, at the hub or support point, the displacement is minimal, almost zero, since that's where the rotor is anchored or supported. Recognizing these characteristics helps us understand how the rotor behaves under bending loads, which is critical for designing turbines that can withstand these stresses while remaining efficient and reliable. Let's take a closer look at the physics behind this phenomenon. When the rotor is at a standstill after prolonged operation, the heat transfer in the concave part of the rotor is actually lower than in the convex area. This difference in heat transfer causes a temperature imbalance across the poles. The hotter pole, which is typically the one with less heat dissipation, will expand more in the axial direction. As a result, this uneven expansion causes the rotor to bow in a specific direction. Now, connecting this to the overall theme, understanding these heat transfer and deformation issues is crucial for designing more reliable and durable compressors. That's why the between-bearing design in our compressors is so important. It helps manage these thermal effects and maintain rotor stability, even under challenging operating conditions. In this slide, we see that the bull gear sag, which is also known as transient thermal bow, has been observed. This sag indicates that the gear is deforming slightly due to thermal effects, which can lead to an unbalanced condition. When this happens, we typically notice a high 1x vibration, meaning the vibration frequency matches the rotational speed of the gear. This imbalance doesn't just stay isolated, it also impacts the high-speed pinion shaft, which is comparatively lighter. As a result, we see increased vibration levels on these shafts as well. Understanding this behavior is crucial because it helps us diagnose potential issues in integrally geared compressors early on, ensuring we can take corrective actions before more severe damage occurs. In this slide, I want to highlight how we detect thermal bow during testing. One key approach involves comparing phase and amplitude measurements at the first bending critical speed. Specifically, we look at the midspan unbalance response of the rotor and compare it with a hot restart conducted up to full speed. This helps us identify any deviations caused by thermal effects. Another method we use is comparing two slow roll vectors from two different starts, observing the intervals during the spin test. This comparison allows us to see how the rotor behaves under varying conditions and detect any anomalies related to thermal bow. Finally, we calculate what we call unbalanced shifts of the mass center using the formula 4U/W. This calculation is crucial because it can be measured with a displacement probe, which is part of the mechanical run test mandated by API 617. Overall, these techniques help us ensure the rotor's integrity and performance by accurately detecting thermal bow effects. When it comes to detecting thermal bow during testing, it's important to focus on specific details for centrifugal compressors. If the compressor has an interstage labyrinth tooth made of a hard material like steel, we need to pay special attention to the hot restart test during the mechanical run test. This is because the thermal bow can be more pronounced in these situations and might affect the compressor's performance or integrity. However, if the compressor's interstage labyrinth or balance drum is made from a rub-tolerant material, then the hot restart test isn't typically necessary. This is because these materials are more tolerant to the thermal stresses that cause bowing, reducing the risk of issues during operation. For integrally geared compressors, the same detection method applies. The key is to follow a consistent approach for identifying thermal bow, ensuring reliability and safety across different compressor types. Overall, understanding when and how to perform these tests helps us maintain optimal performance and prevent potential failures related to thermal expansion. Today, I want to talk about the detection of rotor transient thermal bow. This is a critical aspect when it comes to maintaining the health and performance of rotating machinery. Essentially, thermal bow occurs when uneven heating causes the rotor to bend slightly, which can lead to operational issues if not detected early. Transient thermal bow refers to the temporary, or changing, deformations that happen during thermal loading or cooling processes. The key point here is that early detection of these transient conditions allows us to prevent more serious and permanent damage later on. By monitoring the rotor's behavior in real time, we can identify the signs of thermal stress before they escalate. This is especially important because thermal bow can affect the rotor's alignment, efficiency, and even lead to vibrations or mechanical failure. Connecting this to our overall theme, it's about proactive maintenance and ensuring operational safety. Techniques like advanced sensors and diagnostic algorithms are essential tools to detect these transient phenomena accurately. Ultimately, understanding and controlling thermal bow helps us extend the lifespan of the equipment and improve reliability. Today, I want to talk about the detection of rotor transient thermal bow. This is a critical aspect in ensuring the safety and reliability of rotating machinery. When a rotor experiences uneven heating, it can develop what's called a thermal bow, which causes it to bend or deform temporarily. Detecting this early is essential because if left unnoticed, it could lead to more serious issues like excessive vibration or even failure. In this context, we're focusing on transient thermal bow, meaning the deformation occurs temporarily and can change as the thermal conditions fluctuate. The key challenge is to identify these transient conditions quickly and accurately. Our goal is to implement effective detection methods that can monitor real-time changes, helping us to prevent damage before it becomes critical. This ties into the overall theme of the presentation, which is about proactive maintenance and advanced diagnostic techniques. By understanding and detecting these thermal behaviors early, we can maintain better control over rotor health and extend the lifespan of the equipment. In the design phase, it's crucial to incorporate strategies that help prevent rubs from occurring in the first place. One effective approach is to ensure, as much as possible, that the rotor operates with slow rolling during startup and shutdown. This can be achieved by installing a variable speed drive electric motor, which provides precise control over the rotor speed and helps minimize contact with the stator. We also need to review different bearing arrangements carefully, paying particular attention to the synchronous amplification factor. This factor can influence how the rotor responds to forces and vibrations, so selecting the right bearing setup is key to reducing rub risks. Another innovative technology to consider is the ISFD, or Integrated Squeeze Film Damper Bearing. This technology offers enhanced damping characteristics, which can absorb and mitigate vibrations that might otherwise lead to rubs. Additionally, using rub-tolerant interstage seals and balance drum seals can provide extra resilience. These seals are designed to tolerate minor contact without damage, adding a layer of safety in case misalignments or small contacts occur. But of course, if these strategies don't fully prevent rubs and the situation remains challenging, we need to be prepared with a contingency plan. That might involve a detailed investigation into whether employing a trip multiplier system is feasible. This system can help prevent unwanted trips during startups by controlling the trip settings, allowing the turbine to start smoothly without unnecessary shutdowns. Overall, these design and control strategies are about proactively managing rotor behavior, reducing the likelihood of rubs, and ensuring reliable operation from the very beginning. Let's talk about slow rolling. This technique can really help reduce transient rotor bow, which is that initial deformation you see during startup. The idea is to use the rotor's own weight and rotation to counteract the thermal bow, effectively straightening it out as it begins to heat up. Interestingly, this same philosophy is used in large gas and steam turbines during startup to help manage thermal stresses. Now, slow rolling is possible when we can reduce the driver's speed during startup. For example, with VFD motors or two-spool gas turbine-driven compressors, we can carefully control the speed to implement this technique. This controlled approach offers a way to mitigate bow without risking damage. However, it's important to keep an eye on the bow during slow rolling. If it exceeds a certain allowable limit, our monitoring system can send a signal to the control system. This prevents the machine from proceeding with startup until conditions are safe. In such cases, the rotor system will need to wait for cooling before we attempt to start again. Overall, slow rolling is a valuable method to manage thermal bow, especially when combined with good monitoring and control strategies. It helps ensure a safer, more reliable startup process. Let's take a look at various bearing arrangements. When we analyze the load distribution between pads in a 4-pad bearing, we find that the system tends to have a lower amplification factor or a higher logarithmic decrement. Now, this is an important point because a lower amplification factor generally indicates less vibration amplification, which sounds good at first glance. However, it's crucial to remember that this shouldn't be the sole factor in choosing a rotor bearing system for a turbomachine. In older editions of API 612, which pertains to steam turbines, there was actually a limit on the amplification factor. The goal was to prevent tip clang, which is a type of vibration issue at the blade tips. So, while the dynamic characteristics like amplification factor are important, they must be considered alongside other operational and design factors. And to give you a reference, this understanding comes from the Fluid Film Bearing Fundamentals by F. Zeiden, published in 2011. So, in summary, while bearing arrangement and their dynamic response are key considerations, they are just part of the bigger picture in rotor bearing system design, especially for critical machinery like turbines. Let's talk about rub-tolerant interstage seals and why they matter. During operational events like startup, shutdown, or even if there's a slight misalignment, these seals play a crucial role. The material of the seal is designed to flex or abrade sacrificially, which means it absorbs the impact instead of transferring it to more expensive rotating components. This sacrificial action helps protect vital parts of the machinery. The flexible teeth of the rub-tolerant seal are particularly important. They can momentarily deflect to absorb shocks and then rebound back to their original shape. This flexibility allows the seal to handle shaft movements effectively. By resisting damage from shaft movement, these seals contribute to longer intervals between overhauls and lead to reduced maintenance costs. Essentially, they help improve durability and reliability, which ties into our overall theme of optimizing operational efficiency and minimizing downtime. On this slide, we're looking at what we call the trip multiplier, which is really about understanding how rotor vibrations can escalate under certain conditions. When the rotor passes through its first bending mode resonance, the vibration amplitude can become significantly larger than normal. This is a critical point because such resonances can lead to very high vibration levels that might threaten the machine's integrity. Now, during steady-state operation, We have fixed alert and danger alarm levels that are generally appropriate for normal conditions. But things change when the rotor develops a bow and starts passing through its first bending mode. In this scenario, the rotor's behavior is quite different, and the risk of damage or failure increases. Because of this, the system can actually trip, meaning it's shut down, to prevent damage. What's important here is that we don't just rely on the standard alarm levels. Instead, we introduce a time delay with higher alarm and trip thresholds specifically for these cases. This delay helps us avoid false trips during transient or less critical events, giving the rotor a chance to pass through the resonance safely if it can. The concept of the trip multiplier is supported by insights from Steve Sabin's write-up in Orbit Vol 26, back in 2006. Overall, this approach helps us manage the delicate balance between protecting the machinery and avoiding unnecessary shutdowns, especially during complex dynamic conditions like resonance. And finally, I want to point your attention to the website www.sumisol.com. This is our main platform where you can find more detailed information about our solutions and services. It's a great resource to explore further, whether you're interested in technical details, case studies, or reaching out for support. Remember, our goal is to provide comprehensive solutions that meet your needs, and this site is designed to be your go-to hub for all that. So, I encourage you to visit it regularly and stay connected with us for updates and new offerings. Our areas of expertise encompass a wide range of specialized services designed to ensure the optimal performance and reliability of turbomachinery systems. First, we have structural and rotor dynamics. Here, our expertise lies in finite element analysis, modeling, and simulation of rotating machinery structures and rotor systems. This helps us predict how these components will behave under various conditions, ensuring they operate smoothly and reliably. Next, we focus on vibration analysis and diagnostics. We provide comprehensive vibration monitoring and troubleshooting capabilities, which are crucial for early detection of issues that could lead to failures. By analyzing vibration data, we can identify problems before they escalate. Moving on, our reliability assurance services involve thorough studies and solutions aimed at guaranteeing the long-term performance of your equipment. This includes failure mode analysis and developing predictive maintenance strategies to prevent unexpected breakdowns. Then, there's optimization and performance enhancement. We work on refining the design and operation of turbomachinery to boost efficiency, reduce energy consumption, and extend the lifespan of critical assets, ultimately saving you money and improving operational uptime. Lastly, we offer training and knowledge sharing. Our comprehensive training programs and technical resources are designed to empower your engineers and teams with the best practices and deep expertise needed to maintain and operate equipment effectively. All of these capabilities tie back to our overall goal, helping you achieve maximum performance and reliability in your machinery, which is vital for your success. For more information, visit us at www.sumisol.com.